Hello, y'all. Welcome to lesson 101 of my DB chemistry curriculum. Today we're doing reactivity 3.1.2. It's an HL topic. We're going to talk about the pH of a salt solution depends on the relative strengths of the parent acid and parent base. We'll be able to construct equations for the hydrolysis of ions in a salt and predict the effect of each ion on the pH of the solution. So, with that said, let's go right into it. One of the first parts about this is that when we look at salts, we know that salts are produced by neutralization, by neutralization, which are acid-base reactions. But the thing is, they aren't all neutral. So we have to figure out how we can tell which ones are going to be acidic and which ones are going to be basic. The best way to do that is to start by looking at a strong acid and strong base reaction. So we'll take a classic of hydrochloric acid plus sodium hydroxide. And we know we're going to make water and sodium chloride, good old table salt. Now, the thing is, we know that sodium chloride itself in aqueous solution dissolves, and it dissolves into positive aqueous sodium ions and negative chloride anions. And so what we're going to do is look at each of those reactions with water, whether or not they could hydrolyze water or split water. So we'll react with water. And we can kind of predict what's going to happen here. If we take aqueous sodium and we add it to water, we could theoretically predict, and I'm going to use the equilibrium arrows, that sodium is going to attract the hydroxide, and we'll get sodium hydroxide, leaving one hydrogen left on the water. Therefore, sodium would theoretically produce an acidic solution. But with that in mind, let's also look at chlorine or the chloride ion. Now, when that reacts with water, we would theoretically strip the hydrogen away. And as we strip that hydrogen away, we get HCl, and we're left with our hydroxide, which would make you assume that chloride ions can produce a basic solution. However, this is not exactly what goes on because we already know that sodium hydroxide and hydrochloric acid, these are strong, which means they fully dissociate. So if I were to actually rewrite these equations right here, and I'll write them right down here, I would do that without these equilibrium arrows. Because I know sodium hydroxide will actually dissociate, forcing the equation this way, and I know hydrochloric acid will also dissociate, forcing our equation backwards as well. So this truly shows us that both the sodium and chloride ions are going to be part of a neutral solution because they will not split the water to produce either the hydrogen ions or the hydroxide ions. So we can say, therefore, NaCl, and by this measure, all strong acid, strong base salts, so all of them are neutral. So with that context in mind, let's now look at something that's not a strong acid, strong base. Let's look at a maybe strong base plus a weak acid. So we can take an example of any salt. Maybe we take sodium hydroxide as our strong base and we add it to ethanoic acid, CH3COOH, a weak acid. And when they react in our neutralization reaction, for which we will use a standard forward arrow, we of course are going to get water and our salt, sodium ethanoate, CH3COO. So we now have our salt right here, and that salt will dissolve in water. So as we look at our salt, we have Na plus plus CH3COO minus. That is in our solution. We can then look at the hydrolysis reaction for each of these. Now, we already know that sodium is not going to have a reaction. So what we would say is we would say no acid base activity. That's how we would talk about sodium or chloride. The ethanoate, on the other hand, we know this comes from a weak acid with a acid dissociation constant. When we add it to water, we do in fact get an equilibrium reaction where we're going to have that hydrogen from the water be stripped off the water and added to our ethanoate to once again make our ethanoic acid, leaving us with hydroxide. As we are left with hydroxide, we will therefore have a pH that is going to be greater than 7. So the salt of the weak acid and strong base will still result in a solution with a higher than neutral pH because we have formed a hydroxide. We actually know from equations that our Ka for this would be about 1.8 times 10 to the minus fifth, meaning that we are actually going to produce a lot more hydroxide from the ion. All right. So moving forward, instead of a strong base weak acid, let's now do a strong acid plus weak base. So in this example, it should be probably the opposite if you can take a guess. So we'll just go straight into the example here. We'll look at ammonia, NH3, plus hydrochloric acid. In this reaction, in this neutralization reaction, we'll make ammonium, NH4 plus H2O. Oh, sorry, not H2O. Apologies, plus our anion, Cl minus. As we look at this, we know once again that Cl minus, we can use the same phrase we used before. There is no acid-base activity. We learned that in our first example. So instead, we're just going to focus on the ammonium, NH4 plus. When NH4 plus reacts with our water, it will donate that hydrogen it has to form ammonia again, NH3, and our hydronium ion, H3O plus. Because our hydronium ion is a product of this reaction and it is an equilibrium reaction, we will now realize that we have a pH of less than 7 because we've produced hydronium in solution. So, lastly, what we'll move on to is what if we have a weak acid and a weak base? Won't do too many calculations for this one, or actually not really any at all. But what we can tell is that this is dependent on the dissociation constants, so Ka and Kb of our respective ions. We need to know which ones are going to be more reactive with water, which ones have a higher potential to hydrolyze water. What we generally find is that if these values are similar, if values are similar, the salt will have a pH of approximately 7. So generally, we're just tend to look at whether or not they're similar, and we can make an assumption based off that. The last thing I'm going to go over is, well, how are you actually going to see problems like this worked out on your DP exam? And it's pretty straightforward. They will just ask you to calculate the pH of some solution. So in this case, we'll say 0.10 mole decimeter cube inverse of potassium ethanoate. for which you'll probably get the formula. And what we will also get for this equation, as we need it, is we'll get the Kb at approximately 298, which is equivalent to 5.6 times 10 to the minus 10th. This is, of course, for the ethanoate ion. With this reaction, generally you'll have built up to it. Potassium ethanoate will likely be the product of a neutralization reaction that you'll work out earlier in the problem, and this will just be 1 to 2 marks from that, probably a little more. So the way I'm going to start this one is I'm going to take our ion, CH3COO, and I will react it with water just so that I can keep in mind what I'm getting, for which I will get CH3COOH, ethanoic acid, and my hydroxide. Checking to make sure it's fully balanced, and it is, I'll turn this into an ice table. This is an equilibrium, which means it's always a good idea to do an ice table. Oops, just give myself a little more space here. I know I start with 0.10. I'm going to lose some value x, and I will end up with 0.10 minus x. However, because my KB is so small, and we learned in the last video when doing calculations, especially when it's small, we can just get rid of that x, and we can just assume our initial and equilibrium concentrations are identical. Now, with that, we will start with 0 of each of our products. We will add x, and we'll get x and x. Setting up my equilibrium constant equation, I can see that I have the concentration of ethanoate, ethanoic acid, times the concentration of hydroxide, divided by the concentration of ethanoate, which I forgot my minus on, CH3COO minus. I will now plug in my values, finding that I have 5.6 times 10 to the minus 10th, confirming that's true. And that is set equal to x squared, because both of these are x, divided by 0.10. Rearranging this, I find that x is equal to the square root of 5.6 times 10 to the minus 10th times 0.10. Solving for x in my equation, and I get 7.5 times 10 to the minus 6. This is our concentration, so it will be moles decimeter cube inverse. Looking at this, this is our concentration of hydroxide. So if I have concentration of hydroxide, I can find POH, which will be equal to the negative log base 10 of that concentration. Just plugging that number into my calculator, I'll find that my POH is equal to 5.1. Lastly, I can take my POH, because I know POH plus pH is always equal to 14, and rearrange to get pH is equal to 14 minus 5.1, giving me a grand total of 8.9. And there we go. That is the pH of the salt of potassium ethanoate at a concentration of 0.10 mole per decimeter cube. Anyways, I hope this helps, and have a great day.